Howdy folks, all right, picking up here with chapter 8. So we are going to really start getting into it and applying this quantum mechanics business to real practical physical systems, okay? So the first problem that we're going to do here is the very famous particle in a box problem, okay? Sometimes this is also referred to as particle in an infinite square well. All right. So here's our box. Okay, right? So we're establishing this is a one-dimensional box. So the particle is free to move, to the right or to the left. Okay. And we will say that the potential energy inside the box is 0, and the potential energy outside of the box is infinite. So this is where this is also sometimes referred to as an infinite square well. So this is, a well that our particle is trapped down in. And because it's infinite potential energy outside of the box, the particle can't escape. So we often will say this particle is confined to this box, okay? The particle is confined to the box or the infinite square well, okay? Well, here's what we know already. We actually already know a fair amount about this particle in our box, okay? So we know the Schrodinger equation, right? H psi equals E psi, okay? And so if I expand on that, right, recognizing here that my Hamiltonian operator, right, is going to be negative h bar squared 2m times the second derivative. And because we're saying the potential energy is 0, right, I can ignore that for now. So this is all kinetic energy, okay? So we've solved this problem already, right? We did this in the chapter 7 lecture notes, okay? And when we used the ansatz method, we got all imaginary solutions, okay? Which means our general solution for the wave function can either be written as AE ikx or b times e to the negative ikx, all right? It can be written as a to the e ikx plus b e to the negative ikx, okay? Or, I'll say, either of these are correct because we know that we can convert sines and cosines into e to the ikx's and e to the negative ikx's, and vice versa, okay? So we can use either one of those solutions, and I'll show you which one we'll use as a matter of convenience. We also get that now the eigenvalue, right, E energy equals this, k squared times h bar squared divided by 2m, all right? Now, I didn't quite show you, we didn't quite get into that eigenvalue in the previous slides. What we came more of, what I was more interested in showing you is that solution for k. So we established that k is a collection of all of our constants, right? And that was equal to 2me divided by h bar squared all square root, okay? So we can rearrange that for e, and that gives us our eigenvalue, okay? So the eigenvalue in terms of energy can be written as such, or the eigenvalue in terms of wave number can also be written that way, okay? So these are all things that we've established. So now what we want to do is we're going to pick on the sines and the cosines function to play with for now, okay? So we need to solve for a more specific wave function. So this is a general solution, but we need to find a specific solution. And that specific solution is going to be for our boundary conditions. And our boundary conditions are established by this physical picture, okay? So here's what we know with the boundary conditions, okay? The potential energy is infinite at x less than or equal to 0, as well as x greater than or equal to L, right? So in other words, outside of the box, the potential is infinite, but we know that the potential is 0 for x, let's see, greater than or equal to 0, or really I should say for x between 0 and L, right? So potential energy equals 0 for when x is between 0 and L. So what this also means is the value of psi when x is equal to 0 must be 0. Okay? Similarly, the value for psi at x equals L also must be 0. So that's part of confining this particle to this box. We're saying the wave function, in other words, the particle, can't exist outside of the box. All right? So now if we plug in these boundary conditions, okay, so if we say psi of 0 now equals c, right, times the sine of k times 0 plus d times the cosine of k times 0, what do we get? Okay, well, look, I put a little sine graph right here just to remind us that the sine of 0 is 0. Aha. So that means this whole thing drops out to 0. Well, what about the cosine at 0? Well, recall here, so that this is sine of x, so cosine of x is shifted 90 degrees, right? So that looks like this for my cosine, okay? And now we can see the cosine at x equals 0 is 1. Well, we know that the psi of 0, this whole thing has to equal 0. Okay? So what this tells us is this d constant has to be 0. Okay? Because once again, psi of 0 has to be 0, as given by our boundary condition. We know the sine of 0 is 0, so that drops out that whole term. The cosine of 0 is 1, so that tells me that this coefficient d has to be equal to 0. Okay? So now we'll reestablish that we know that psi of x has to equal c times sine of kx. Okay? We know that when x is 0, sine of 0 is 0, so that's good. We've established that boundary condition. Okay? And so now what we also have to say is psi, when x is equal to L, we know that has to be 0. So that's going to be c times sine of, and I'm going to replace the x with L, KL. And we know that that also has to be equal to 0, all right? And further, we know this c constant cannot be equal to 0 because we have to have this normalization constant there. So what's going on with this thing? Okay, so how do we solve this sine KL equals 0? Well, we can say that the sine of k times L has to equal 0. I don't need to worry about my c coefficient, my normalization constant, okay? And now if we go back and look at the sine graph here in the red for a second, look, we actually already have the solutions, okay? So we know that sine is 0 at x equals 0, right? At x equals 1 pi, at x equals 2 pi, 3 pi, 4 pi, etc. Okay? So what we can say now is this quantity, k times L, has to be some integer value of pi in pi. And specifically, because we can't have n equal to 0 because we've already established that up there, psi of 0. And we also want to establish this for positive numbers, okay? We're going to say that n equals 1, 2, 3, 4, etc., because now, right, for each KL, if KL equals 1 pi, we know that's going to make it equal to 0. If KL equals 2 pi, well, that's also going to make that equal to 0, okay? So now, not only have we established solutions, but we've established solutions for various integer values n. So let's keep going with this, okay? So now what we can finally do here is say, well, KL has to equal n pi, all right? But we know that that's also got to be, so if I rearrange here, now that means this k is going to be equal to n pi divided by L. It still also equals this, okay? That hasn't gone away. It still is equal to that, but we're going to see that we can combine these results algebraically. And so now if we know one way to write k is n pi over L, then we can write this wave function as c times sine of n pi over L times x, okay? Where again, we remember that n is 1, 2, 3, 4, etc. Okay? We're going to see there's special significance to this n, and it should look familiar. Maybe you recognize that as principal quantum number n. Principal quantum number. Okay. I'm going to come back full cycle around this. This is exactly the n that you are thinking of. Back to your general chemistry days, right, for 1s, 2s, etc. And we're going to connect how that has established itself as this principal quantum number, okay? It's a solution to the Schrodinger equation. So now we have to normalize this wave function for that c constant, okay? And so let's do it. So recall, and we also want to normalize this specifically to our boundary condition, all right? So I'm going to establish this normalization constant over the range 0 to L, right, as given by the length of my box, okay? And that's going to be the square modulus dx. And then I'm just going to keep using the same letter just to not confuse it. So we know that that's going to be c squared in front, and that all equals 1, all right? So now plugging all of this in, I'm going to have c squared times the integral from 0 to L. And we can just make this sine squared, okay, square modulus. So that's going to be sine squared of n pi x divided by L dx, all right, all equal to 1. And as it turns out, that has a standard solution. So the integral from 0 to L of sine squared n pi x over L is a very easy solution. So all of that is just equal to L divided by 2, that whole integral, all right? So then there's still times the sine squared equals to 1. And so now rearranging this here for c, right, this becomes, so multiply 2 over L, take the square root. This becomes the square root of 2 divided by L. And so now I'm going to write this new wave function here as psi. And I'm going to write here a capital N to tell me that it's been normalized. But I'm also going to put this lowercase n to tell me that I've got this new wave function that's dependent on this interesting integer, this quantum number n. Okay, so now 2 divided by L square root of sine n pi x over L. And this is my wave function for, so my normalized wave function for a particle in a one-dimensional box. And then, of course, so this is only over the range 0 through L, right? Because outside of the box, the particle can't exist, okay? So what do we get from all this if we keep going? So we established this kind of funky N, right? So what I also want to show you, very quickly, if I back up here and I look at the eigenvalues, okay? So we also know from this solution that E equals K squared divided by, or K squared times H squared divided by 2M, where K equals this 2ME divided by H squared, okay? Well, we also established from this that K equals, where did it go? I lost it. That K equals N pi over L, okay? So if we combine those two things, so K equals N pi over L, but it also equals 2ME over, and I'm going to write this as, instead of H bar squared, I'm going to write this as H squared over, so that would be 2 pi squared, which would be 4 pi squared. And we know that's all square root. Okay, I'm going to do some algebra and rearrange and solve for E here. And I'm just going to show you that solution on the next slide. Okay, that we have right here. Okay, so once again, where did that come from? So that came from the fact that we know K equals 2ME over H bar squared square root. But we also know that that equals N, what did we say? That it's N pi over L. All right. So instead of writing here H bar squared, remember H bar equals H over 2 pi. I'm just using H here because that way we can cancel the 2 pi's, right? There's a pi on this side of the equation, and there's a pi buried in that Planck's constant, okay? Those all cancel. And now what we get is energy as a function of this number N goes as N squared, H squared divided by 8mL squared for the normalized wave function that we just came up with between 0, x, and L, okay? And so you notice that I've got a couple pictures going on. Here I've got this picture right here. But I've also got this graph, right, that's going to be your Mathematica 3 assignment. And I want to show you through this manipulate function what's going on when I change this value of N. And so for now here, I'm just looking at a box that has length of 2 pi, okay? So, and then you can see the same established graph right here for this case where this is 1. So that's N, the values of N right here, okay? And so now as you can see, when I add another value of N, of course it didn't update for me. So let's evaluate this notebook here. Okay, great. So now when I go and add values of N, so I make N equal to 2, look at that. I get another period there. And now when I add N is equal to 3, I'm getting another one, and another, and another, and another, and another. Okay, so I'm getting these integer values. Okay, we will see in the coming slides that this E as a function of N, these are very much related to the energy levels of particles, or the particle in the box. Okay, so we established here that the only energy that we have in this box is kinetic, because V is equal to 0, okay? But so this is the solution to the kinetic energy, K squared H bar squared divided by 2M, all right? So it's that same energy. We know that's its only energy, which is kinetic. So what we're seeing, what's really cool about this is that kinetic energy does not have continuous values, rather it has quantized values. So in other words, when N is equal to 1, we know it has the value of H squared divided by 8mL squared. However, when N is equal to 2, it goes up by the square. So now that N is equal to 2, right, becomes 4 times H squared divided by 8mL squared, When n is equal to 3, it goes up by the square again. It goes up to 3 squared is 9 times h squared divided by 8ml squared. Okay? So we're going to see some pretty cool implication from this. And so we establish here that these n values make up different quantum states. And the reason why they make up different quantum states is because they're a different eigenvalue. Each time we change the number n, we get a new eigenvalue. So in other words, psi of 1, plugging into this function, right? Psi of 1, square root of 2 divided by L times sine of pi xl, that describes one state. But when n is equal to 2, okay, that's now going to be sine 2 pi x divided by L. That's going to be a new state. And these states are quantized by this level n. Okay, so I want to keep going with this and pose a question. We need to consider if this solution is an acceptable eigenvalue equation. So this solution specifically, okay? So one way that we could do that would be by using the momentum operator and operating on psi and seeing if we get a single eigenvalue out of it. But we won't run into a problem almost right away. Check this out. If I go h bar over I times d dx of this equation, which we know is root 2 over L, times sine n pi x divided by L. So remember, when I carry out this operation, it's supposed to return to me an eigenvalue, but also it's supposed to return the original function. So in other words, what that means is I'm going to have to get here some eigenvalue that I'll represent by omega, but then I'm going to have to get back my original sine m pi x divided by L equation. And hopefully you can see right away that's not going to work because the first derivative of sine is cosine. So this becomes a problem. Is it a problem that we can correct? The short answer to that is yes. And we can correct this problem by using the Euler Relations, okay? So in other words, now if we reimagine this wave function that we've come up with, here it is, the wave function for our particle in a box, okay? I can rewrite sine as the following. So 1 over 2i times that normalization constant times e to the ikx minus e to the negative ikx. So this is the same two equations, okay? And now what's really cool about this, look at this. This is a linear combination of exponential functions. That means it's a superposition, which is really cool. And what's also really cool about this, we've already established using this generic wave function, right? E to the ikx plus b e to the negative ikx. I know that these aren't quite like in the same form, but as far as like a general solution, they are. They're in the same form, okay? So what's really cool is we established earlier this notion of e to the ikx and e to the negative ikx. That describes a superposition of particles moving left and right, okay? So the psi plus state, right, we know describes particles moving to the right. The psi minus state, of course, describes particles moving to the left. So just built in naturally to this function, this sine function that I'm going to separate right here, this already describes a superposition of eigenstates. So this error that we ran into here, yeah, that's an issue, but it's an issue that we can basically move right past. If instead of thinking of this as a pure sine function, we recognize that really this sine function is a superposition of these eikx, e negative ikx functions, which we also established describes particles moving left and particles moving right. And this gets even cooler now. If you're following with me, I hope that you are. Stick with it here. if now we were to look at the expectation value of particles in my box, okay? So I'm establishing here the sign using the same wave function, okay? And we could use the sine version or we could use the superposition version. It doesn't matter because we'll get the same result. The expectation value for the momentum of the particle in my box is 0. Does that make sense? Well, I think it does, because if I look at my particle right here, okay, we know that the particle is free to move in either direction. And we established here when n is equal to 1, so here I'm showing you the wave function. But now if I just go past this and I look at the wave function squared, right, we know that it's all positive values. Look, that wave function squared is telling me the most likely place to find that particle is right somewhere in the middle. So why is it that the expectation value of its momentum is 0? Well, that's because it's moving perfectly in this direction or in this direction. And those two different directions, the positive velocity and the negative velocity, cancel each other out. And so you have no net momentum. We expect the particle to be found right in the middle of the box. And then, of course, there's diminishing probability on either side of that. Okay, very cool. So now what about this expectation value of the momentum squared? Well, if we were to carry out the expectation value of this momentum squared, we get n squared h squared over 4l squared. Well, why is that significant? Well, I'll remind you that kinetic energy is equal to p squared over 2m, right? That's another way of writing 1/2 mv squared. Check out what happens to this result. So the expectation value of this particular wave function, right, is n squared h squared over 4l squared. So let's write that down. N squared h squared over 4l squared. Well, now, so what happens if I take this value and divide it by 2m? What do I get? Well, I get n squared h squared over 8ml squared. And look at this. It's exactly what we got from the Schrodinger equation. So all of this that I'm kind of spinning the gears, going round and round and round, is to establish that this is a good solution, that we can work with this solution, all right? It also establishes this notion that we expect our particle to exist somewhere right here in the middle, okay? And as I go up in different energy levels, okay, I still preserve this symmetry of superpositions of particles moving perfectly left or perfectly to the right, okay? And so I think I've kind of got that described here on the next slide here, right? If I look at psi squared, right, that function, so you can see it's kind of establishing the same thing that I'm showing you here with this picture. And, you know, keep in mind, we're talking about a particle that's moving like back and forth, right? And so something really cool to this, or something really cool happens when we really crank up this n value. And I want to demonstrate that over here. So in my little simulate, I'm allowing n to go from 1 to 10, every unit of 1. So you can see it maxes out at 10, okay? What if I allowed it to go up to, you know, like 1,000,000? And I'm not going to say every one. Let's just let n scale all the way up to 1,000,000, okay? What does that look like if I do that? Well, it looks like basically the particle can exist anywhere along this path, which is actually what you would expect from classical mechanics. If we're imagining classical mechanics, our particle is just moving back and forth, right? We expect that it can exist anywhere along here, okay? Well, look, if I make the n principal quantum number, if I make that 1,000,000, these probability distributions show that. And even if I go way down to, like, you know, 400,000 or 200,000, right, at these humongous values of n, it's basically just showing that the particle can exist anywhere along the box. Not until I get down to these very small values, like 1 or 2 or something like that, do I get these quantized exact positions where I expect the particle to exist. So that is what we call the correspondence principle, which states that classical mechanics emerges from quantum mechanics as large quantum numbers are reached. Okay? And so what I also want to go back, I'm going to go a little bit over my 30-minute movie. You may have seen this GIF that's on our course homepage. This is the particle in the box problem, right? You've seen in that GIF how this particle is kind of bouncing back and forth in the box. You've seen how these solutions are evolving. So those are actually showing you the how these wave functions will evolve in time. So A, B, and C show the standing wave approximations. Panels E and F show us the actual full time solution, which is really cool. I've got a Mathematica file here that Wes Bliven hooked me up from physics. And I'll just point out one of the small elements. So here we go, e to the negative I t. So that's really the only thing that changes in these wave functions with respect to time. You can also see another function right there, e to the negative I energy I squared times t for time. So this is really cool now. So this is psi squared of our particle in the box. And what we're going to see this particle move back and forth in this box. But we're going to see what it looks like when the wave functions are evolving in time. And so let's push play. Yeah, I'm going to make it go nice and slow. And so this is really cool. We're going to see this, this particle, all it's doing is just moving back and forth. But it looks crazy because there's a confluence of constructive interference and destructive interference that's really making those wave functions appear quite funky. So I think we can speed up the time a little bit on this thing. So there we go. So it's just, honestly, this is all it's doing is just a particle that's moving back and forth as a superposition of exponential functions with imaginary exponents. Okay? So this is kind of cool. Okay, so one last little bit to go through, and I'm going to end that off. Okay, so let's talk about these energy levels. Okay, so we noted here for my psi function, right, for the particle in the box, normalized. All right, this is writing psi lowercase n, right? But just to remind you, if I wrote psi uppercase n, comma psi lowercase n, to me the uppercase n tells me it's been normalized. The lowercase n tells me we're dealing now with this new quantum number thing. Okay. So we note that energy goes up by the square, and you can see here are these values of n, right? When n is 1, it's just 8 squared over 8 ml squared. We call that energy level the 0-point energy, okay? Because, as it turns out, right, there's no temperature in this equation. So what that means is, even at 0 Kelvin, we would still have this 0-point energy. So it's our ground state, okay? The ground state, all right? So when n becomes 2, right, that goes up by the square. So, right, it goes up to 4. And then when n equals 3, it goes up by 9. And then when it goes up to 4, it goes up by 16, etc. It keeps going up by the square. Now, each of these levels become our quantized energy levels. And this creates the basis of what we know about quantum mechanics, of energy only existing in these unique quantized values, okay? This shaded area, right, that's kind of showing you this region between, those are the classically allowed energies. So in other words, if we just truly had a particle, like a little marble, right, rolling back and forth, okay, it could establish any value of energy along the scale. In other words, that value n wouldn't exist, okay? It would have no value of n. However, because we established this using the Schrodinger equation, we got this quantized solution, quantized by this level n, all right? And so, of course, we can do some quick algebra to also calculate the difference between any one energy level, right? So if I put in En plus 1 minus En, okay? So now replace n with n plus 1 squared and just do some algebra. We get this factor 2n plus 1 times that quantity h squared 8ml squared, okay? And so this quantity 2n plus 1 is going to come up later on as well. But this is allowing us to establish an easy way to calculate the difference between energy levels. And so what I want to point out a couple things. So here I'll write delta En equals 2n plus 1 times, I wanted to write h bar, but that's just regular h squared over 8ml squared. So what happens as n goes to huge quantum numbers, okay? Well, we established classically if n goes to humongous quantum numbers, okay, this is approaching that of a classical system, all right? And so as n goes to these humongous quantum numbers, you know, it's 2 times n plus 1. Well, that plus 1 no longer matters, okay? So it's not as significant. So now, on the other hand, what if we made the size of the box really big? So this is another thing we could do. We could keep the value of n fixed, so we keep it on the same quantum number. But what happens if we really stretch out the box, if we make the box bigger, okay? So I can do that over here. Let's go back to the n is equal to 1 example. And now on my manipulate here, this L, I can make this L bigger. And I've fixed the scale on this thing, so you just kind of have to watch this carefully. But now, as I'm making the box bigger, look what's happening. The wavelength is getting bigger, okay? So as the size of our box gets bigger, the wavelength gets bigger. So what does that mean for quantum mechanics or classical mechanics? Well, there's some really cool things that I'm going to show you at the conclusion of some of these slides, that there are physical colorimetric observations we can make. So as the box is getting bigger, our wavelength is getting bigger, meaning our energy delta E, the difference between energy levels, is getting smaller. And so what you actually see in real life, in practical terms, as the particle in the box gets bigger, its spectrum will redshift. As the particle of the box gets smaller, its spectrum will blue shift, right? A bigger box means a bigger wave, which means a more red color. A smaller box means a smaller wave, which means a more blue color. And we can actually observe that in spectroscopy, which is very cool, okay? But if, let's say, the length of this box, if we got it so big to the point where we're not talking about the size of an atom, but we're talking about like making the box the size of a room, right? Let's say we do particle in a box, but now my box is this gigantic room-sized box. Well, the delta E would become so small that our energy levels would blend together and it would look like classical mechanics. So once again, we would get the correspondence principle, okay? So there are huge differences when we talk about putting an electron in a box where the box is the size of an atom versus if we put an electron in a box and the box is the size of a room, okay? The bigger that box gets, the more it approaches just a classical mechanics picture. Okay, folks, that was a little long. Apologies for that. I'll see you in the next one.